last time we were talking about particle in a what size box? Yeah. In a 3D box, we're actually going to see some connection to the orbitals that you guys know from general chemistry that you've probably painstakingly considered in organic chemistry and that you're being forced to remember back in inorganic. So we'll actually see something that looks a little chemical out of this in a bit, but we have to do some derivation of it. We said that we have a box. What's the potential on the inside of the box? 0. What's it on the outside of the box? Infinite. And then what did we say about the walls? Because the walls matter. Yep. Stuff can't get through them. They're impenetrable. So we're going to describe that system. We came up with the generic Schrödinger equation. And then we had an applied Schrödinger equation, right? The potential energy term dropped out. But what did the kinetic energy term look like? Mm-hmm. Yep. So and what does psi depend on in this case? Yeah. And we got that far, right? Did we describe another way we can represent this with a different symbol? Oops. What was it? Yeah, the gradient. So sometimes you'll see it like that. It's really crappy because my chalk broke. But an upside down delta is typically what we use. So anytime you see that, it's really this, and it's just shorthand for it, so we don't have to write it a million times. Okay. So we have our applied Schrödinger equation. What do we need to do next? Or what have we done with our other quantum systems we've looked at? Well, what do we want to know out of this thing? Yeah, we want to know the wave function. So we got to try to find the wave function. All right. We're going to make an assumption, and we'll see that this assumption works out in a little bit. What does psi depend on again? Yep. So it's a function that depends on all of those. Is that an ideal situation? No. What would an ideal situation be for us? Yeah, it depends on one variable. What we're going to assume is we can separate this wave function out into smaller wave functions that only depend on one variable. So we assume psi can be broken up into okay, what would we want the first function to depend on? X. We're going to give it the symbol fancy x. What about the second function? We'll call it fancy y. And then finally, fancy v. Z, excuse me. I always put a line through my z's because my penmanship's horrible. So that way you know it's a z. I didn't start doing that until I started writing on the board for other people, and everyone just kept on getting confused if I was writing 2's or z's. So I've upgraded. Okay. So now we make that assumption. What should we do next? Yeah, we got to find x, y, and z. How are we going to find that? Or what equation does our wave function have to obey? So everyone's eyes divert to it. What equation does it have to obey? Go for it, Will. Yeah, it's gotta follow this guy, right? The one that we formulated. So let's take this and plug into our Schrödinger equation. So it's going to look a little long. Oop, I changed the way that looked. Put that back. Y and Z. Okay. We have partial differentials along here. And we said that our equation, our wave function is separable. For this term, what's the only function we really have to worry about differentiating? Yep, fancy x. What about for this term? Fancy y. And this term, z, right? So we could distribute these functions through, and we're just gonna, for the first one, get y, z times the second derivative, differentiating that one, right? So, because what's the benefit of a partial derivative? Yeah, these other things are treated as constants when we look at a partial differential. So that's what this red term would look like after we distribute it through. What's the yellow term going to look like? Yep, x, then z, and then what goes in that partial derivative? Yep, y. And then for the last one, what's going to come out front? Yep, x and y. And then z, fancy z, excuse me. And blue, after we distribute that guy through. And that's all equal to this thing again. Okay. This doesn't look like it's easier to solve yet. But each of these is like its own little term, right? So what could we do to the energy? Well, we'll see that in a minute. Let's just put this thing here, even though they're equivalent to one another. Okay. This looks complicated. It does help us, but it does look complicated. What would we want to isolate by itself? We would want to isolate energy by itself. So what would you do with this portion here? You divide it all the way through. That's going to be really beneficial, and we'll see why in a second. So that H bar thing hangs around. When we divide through by fancy X, fancy Y, and fancy Z, what happens here? Or do we want to work it out? Yeah, it's 1 over fancy X. And then second derivative of X. Okay. Now this first term, it had all of those functions in it. But after we do the division through, what do we get here? Just X. What do you think is going to happen with the yellow term? Yep. And then what about the blue term? Yep, just Z. Blue. All equal to the energy, right? Okay. We have separated the variables out for each of these things. And now, if you look, this part's only dependent on X, this one's only dependent on Y, this one's only dependent on Z. The energy is all of them slapped together, right? So we've shown you can separate them out. What could we assume about this energy then? Kind of like you would do possibly for physics when you're considering vectors and other things. Yeah, so you could get the energy from the X portion plus the energy from the Y portion plus the energy from the Z portion. You can separate out those contributions. Okay. So let's say we evaluate like this whole thing together. What are we going to get out of it? I'm just saying for just this red term. Yep. Yep. Then what about just the yellow term times H bar over whatever? Yeah. And then what about that guy times? Yeah. Okay, so what could we do to try and solve for each one of these things? Yeah, let's separate them out. We can have isolated equations for each of these things, and then we can think of an eigenfunction, eigenvalue that would work for each of them. So let's isolate variables. Is equal to E sub x. We'll do this for the other ones in a minute, but I feel like we should just stare at the x one first. Okay. How does a generic eigenfunction look like again? You have some operator that acts on a function, and what do you get out of that function? Yep. Yep. Does this really look like that generic eigenfunction, eigenvalue problem? No. Is there a way we could make it look that way? Uh-huh. What's this thing? That's a constant. What do we need to have multiplied by that constant to get an eigenvalue, eigenfunction problem? Uh-huh, the wave function. Any way to get a wave function over here? Yeah, multiply this thing through. X, and then what's this side equal to? E sub x times what? Yep, fancy x. Okay, we can do the same thing for the other ones, right? It's almost the exact same thing, except all that changes are fancy x, what we're differentiating by, the energy. In this case, we'd look at y. And we would get z out of this. Okay. Now, how many eigenvalue, eigenfunction problems do we have? Got 3. We got to solve all 3. Crap, that means we have to solve 3. Have we seen this before? What's going to be the mathematical solution to this thing? Where we take 2 derivatives, we end up with a constant in that same function back out. Yeah, sine function. What system would that be that we used sine to describe it? Yeah, 1D particle in a box. So we've already solved this thing before. We know its signs. We went through the formalism for it. We have an eigenvalue problem that we already solved. Which is good. We're going to have fancy x that depends on some principal quantum number, n sub x. So that's the energy level in the x direction. You can tell me what the rest of this looks like based upon the solution to particle in a box. You need to check back in your notes, go for it. Square root of what? Yep. Yep, sine. Right. But since we have three principal quantum numbers, we want to indicate a sub x there. Y, how would that function look? Same thing, but a little different. It's not going to be 2 over a. What's it going to be? Yep, b. So that's the length of the box in the y direction. Then sine, what else do we got? Yep, n sub y, pi. Yep, y all over what? Yep. And then z, we got n sub z, depends on z. What's that one going to look like? Yep. But which one is our wave function for the entire system? Yep, because we said our wave function was equal to that. So all we have to do, let's multiply all these things together, and that will tell us what we have. So all of our normalization constants are going to be pulled out front. We're going to get square root of what over what when we multiply all those things together? Yep. ABC, yep. Times sine. We'll have an x pi x over a. What else do we have to have? Yep, sine of y, sine of z, right? Okay. So now, if you wanted to get a total energy expression, you could show that the energy is only going to depend on the length of the box in each of the directions and what you have for those principal values. So can you guess what you're going to have to do for a daily problem? Yeah. This with numbers, and you're going to have to derive an energy expression. N sub x, n sub y, n sub z is equal to x squared over a squared plus ny squared over b squared plus nz squared over c squared times h bar pi 2n. How are we doing on time? Okay. Cool, we got time to cover some stuff. Okay, so what we did, we figured out what our wave functions were. We used separation of variables to split those systems apart. We're going to try our best to always use separation of variables to get to differential equations we can solve. And we'll see for other systems, like when we get to the hydrogen atom, or systems that depend on more than one dimension, that we're going to have to separate variables. Okay. Are there any questions about this? You should be able to go through this procedure of separation of variables, like mathematically show how to separate those things. We're going to use this tool a handful of times, not for the next system, which is a harmonic oscillator, but for all other systems beyond that one in this class, we're going to need that. Okay? All right, am I okay to erase this stuff?